In this video, we're going to carry on exploring SQL by actually working through some examples. In this notebook, we'll be using SQLite, a particular flavor of SQL, or a particular SQL database implementation, which is useful for demonstration purposes or learning purposes, as well as when we want a quick and easy database for an application where we don't need to store an enormous amount of data. If you are creating an application that only stores a few gigabytes of data, SQLite is a great choice simply because of how easy it is to set up. SQL databases in general are very commonplace. For example, all of your grades are stored in a MySQL database, while all the posts and users on the message board are stored in a Postgres SQL database. And at the conclusion of this set of lectures on SQL, we'll talk a little bit about the differences between the various flavors. But for the sake of this lecture, we're going to be using SQLite. So we'll load the SQL extension for the Jupyter Notebook that will let us use SQL code in the notebook. And we'll create what's called a database connection just in this line here. So typically, and we can see it says connected to testdb.sqlite. And in fact, if we look in our data wrangling directory where this SQL notebook is stored, there's now a new file created just seconds ago that is 0 bytes, so it doesn't contain anything yet. But this is our SQLite database. SQLite is databases are stored in a file, which is very convenient if we ever need to take that database to a new machine or platform. Other SQL databases are much more difficult to migrate. The simplicity of SQLite, again, demonstrates itself. But generally, no matter what kind of database we're working with, we'll start with a database connection. The connection is essentially a connection between our client, where we write queries or commands, and the database itself, where the data is stored and where our commands get processed. So from now on, we'll be looking at cells with this, beginning with this SQL magic, which indicates that the code contained is SQL code and should be interpreted as such by the notebook. Since we've loaded the SQL extension, we're free to use this magic. So we're going to start by creating the tables that we outlined in our kind of pen and paper example or illustrated example. We'll be making a customers table, a products table, and an orders table. So first of all, just in case you're running this example multiple times, we're going to start by removing those tables if they already exist. So we'll be starting from scratch. And once we're sure we've gotten rid of any existing tables, we'll make those tables we were just talking about. And each table is created using the create table command. Then we have the name of the table we want to make. And then enclosed in parentheses, we have what's called the the table schema. A schema is a plan for the architecture or structure of an object. So here we're specifying the structure of these tables. Each line declares a different column in the table. On the left-hand side, we have the names of the columns. On the right-hand side, we have the properties of those columns. So for example, the customer IDs will be integers, and they cannot be null. We must have data there. We cannot create a row in our customers table without supplying a customer ID. Likewise, name and billing address are also not null. They must be supplied whenever we create a row in the customers table. These columns, as opposed to the ID column, will hold text rather than integers. The only property I haven't talked about is this primary key. A key is similar to an index for a table. So in pandas, we identified rows of the table based on their index. A key, likewise, identifies a row in a SQL table. However, a primary key has some restrictions that a pandas index does not. A primary key must be a unique identifier for a row in a table. Therefore, every ID in the customers table must be different. And this will give us a definite way to refer to each row in the table. It's commonplace for most tables to have some primary key. The products and orders tables are defined similarly. The products table has a column of IDs, just like the customers table, but these IDs will refer to different products rather than different customers. And each product will also have a price. Finally, we have the orders table. Each order also has an ID. But since some orders will contain multiple purchases, the order ID is not a primary key. Many rows in our orders table will have the same ID here, because each row refers to a purchase of some item, and some orders contain multiple items. We also include a customer ID and a product ID, so we would know which items are being purchased and by who. These customer IDs and product IDs should be referenced to other tables, meaning we should only be able to create orders for customers whose IDs are present in the customers table. This restriction is referred to as a foreign key. So we will only be able to create rows in the orders table with customer IDs that are present in the customers table. So by saying foreign key customer ID references customers ID, we're setting up a relationship between the orders table and the customers table. This is another important component of the relational data model. We're creating a relationship between our tables using foreign keys. Let's go ahead and run this cell to create these tables. Every time we successfully execute a command in SQL, the server tells us that that command was successfully executed by returning done or printing done to screen. If we were to encounter an error, we would get an error message instead of done. Note, each line of SQL is terminated with a semicolon. Unlike Python, SQL does not use white space to control the syntax of the language. SQL does not care about whitespace in any way. Therefore, it's important to distinguish separate lines of SQL code using semicolons. All these tabs or spaces to align these various properties and column names have no impact on the execution of the SQL code. It's only these delimiters, like the parentheses, the column or commas, and the semicolons, that impact the execution of the code. The visual alignment is purely that, visual. This is a major contrast to Python. So now we've created our tables, and we've defined the structure of the tables, but they're empty. There's no data in them. We can see this by trying to select data from our table. So if we try to select everything, so this asterisk is a wildcard character, meaning anything. So we're going to select any column or every column from our customers table. We see we get back done because the command or query was successfully executed, but it returns just an empty table. Nothing interesting here. We can see the schema in the different column, reflecting in the different column names of the table that's returned, but the table is empty. So let's begin inserting some data into our tables so that we can actually do some real data analysis in SQL. Since we defined the relationship between the orders table and the customers table, and the orders table and the products table using foreign keys, we'll first have to populate the customers and products before populating the orders. We can add data to a table using the insert command. So we'll insert into the customers table, following the column name schema, these various values. So we're saying here that the order in which the values are presented is ID, name, and then billing address. And then we simply have tuples representing the different values we'd like to enter on different rows of the table. Likewise for the products and the orders. Again, the visual alignment here is purely visual. It's common when writing SQL code to adopt certain conventions to help clarify what is a SQL command and what is a name that we have assigned, some arbitrary name we've picked, by putting SQL commands or keywords in all caps, while names are lowercase. Likewise, if a command spans multiple lines, subsequent lines will usually be indented to indicate that line continuation. As we insert values into our table, we not only see done, indicating the various successful queries, but we see how many rows are affected as a result of our queries in our tables. So when we're modifying tables by deleting rows updating data in a row or inserting new rows into the table, SQL tells us how many rows in that table were affected. Here, we inserted 5 products into the products table. Then we inserted 2 orders into the orders table, 2 more orders into the orders table, and finally 3 more orders into the orders table. So we see 5, 2, 2, 3. Admittedly, I'm not certain why this first line didn't say 3 rows affected before the 5 rows affected. But sometimes feedback is a bit of a mystery. Now that we've inserted data into our tables, we can check that the data made it in there successfully. Maybe we don't trust this status information that's been returned, by doing some simple selections. So here we see the data in our customers table, our products table, and our orders table. Keep in mind, just like when we were working with pandas, we often will want to limit the amount of data that we print to screen. So when working with pandas tables, it was common to only show the head of a table so that we wouldn't show hundreds or thousands of rows, which could overload our notebook and simply overloads our mind's ability to easily understand a collection of numbers. We can't really think simultaneously about more than 7 or 10 different items. So we can limit how much gets printed out from a SQL query by using the limit command. So here we have just the first 5 rows of that table. And in practice, if we're simply inspecting a table, it's a good idea to include that limit command. I'm going to, there was one more thing I wanted to mention, actually, which was when we're creating tables, in this case, we chose for our primary keys that we would explicitly specify what these integers are as we insert various customers with their customer IDs and products with their product IDs into those tables. So we said this should be an integer primary key, and we'll say exactly what it is when we add rows to those tables. However, it is possible to set default values for fields that might be null, or for instance to, in the case of primary keys, tell SQL to automatically assign incrementing values. Now, off the top of my head, I might not remember. Yes, I thought it was auto increment. So in SQLite anyway, by adding the auto increment keyword to our primary key definition, we could tell SQL that if we are creating new rows, that primary key should automatically be generated simply by enumerating the rows of the table. So there are more useful options that we haven't shown here, kind of selecting these default values for rows that might otherwise contain null values, or primary keys that should proceed just as incrementing integers. In the next video, we're going to start working with a more substantial data example where I've prepared some customers, products, and order tables in CSVs, and we're going to use pandas to help us load that data into SQL rather quickly.